In this clip, I will show that there's a very strong relationship of f being continuous at some point and the convergence of the sequence of images when we take a sequence converging to that point. What I mean by that will become clear in the next theorem. So I will show the following theorem. Consider that we have f defined on an open interval, and suppose we take an element in that interval a. Then we can show the following equivalence. So we have the following, that f is continuous at I. So this means that if we take x from the domain in I not very far from A, then the images don't differ so much. This is equivalent with the following property, that for any sequence we have which has as a limit A in this domain, so if we take a converging sequence to A, then the images are neatly converging to FA. And this should hold for any sequence. Well, an application of this theorem is the following. Suppose now we take the following continuous function. This function has as domain r except minus 1, right? So this is a continuous on its domain, and domain is given by r except 1 minus 1. And suppose now we take a sequence an, which has a limit n to infinity an equals 3, right? So we know that 3 belongs to the domain of this continuous function, and an, if we kick out all the elements that for which we have the value minus 1, then we obtain a sequence with limit equal to 3, and the sequence that is completely contained in I. Right? So what does the theorem say? Well, if f is continuous at 3, then for any sequence an with the limit 3, we should have that the images, what are the images? Well, the images are the f of an. Well, these should converge to the f of a, which is now 3, so the f of 3. So we can easily calculate the limit, which is now 3 over 4. And we can make such a statement without exactly knowing the sequence an. We only need to know that it converges to 3 to conclude that the images are converging to 3 over 4. I will prove the theorem in the coming. So first I will show the forward implication. Well, let's go back for a minute. What is the forward implication? Well, I assume that f is continuous at a, and then I have to show that for any sequence an with limit a, I should have that the limit of the images are converging to fa. Right, so let's do that. So here I start. So suppose f is continuous at a. What does it mean, right? So in the last video, I gave the precise definition of what it means that f is continuous at some point in an interval. It means the following: let epsilon be larger than 0, which is an arbitrary but fixed positive number. Then we should be able to find a delta larger than 0, which may in general will depend on this epsilon, such that when x belongs to the domain of f and the distance of x to a is smaller than delta, then we automatically have that the images are not so far apart. They differ at most in absolute value. The difference is at most in absolute value epsilon, right? So given a small epsilon, we can find delta small enough so that when x is close enough, then the images are close. So that was continuity, right? Do you recall it? So now we look at some sequence. Now we take a sequence which has a limit a, right? So it's a sequence in this interval, and now we have to show that fan converges to fa. Okay, but the limit of n to infinity of an being equal to a, it means that if we take an index high enough, then we can bring an close as we want to a. We can make it such that the difference between an and a is at most delta. Delta is a positive number, so we can make it. We can choose an index. We can choose an index. There's an index, capital N, such that when we take larger indices, that the difference of an minus a is smaller equal than delta. And this is a very nice property, since look at this one. An belongs to the domain of f, right? So it's in I, and then an can be plugged in here, right? So an, the absolute value of an minus a, is smaller equal than delta, which automatically means that the absolute value of fan minus fa is smaller than epsilon, right? Okay, so by picking n large enough, we see that an minus a is smaller equal than delta, which means that the absolute value of fan minus fa is smaller than epsilon. And this reasoning can be held for any epsilon larger than 0. So in particular, this means that we can find an index, capital N, such that all n larger than n, we have that fan minus fa absolute is smaller equal than epsilon. This means that the limit of n to infinity of fan just equals fa. So this proves the first part of the theorem. The second part of the theorem is the converse. It's a little bit more subtle. We have to show that for any, well, let's go back 2 slides. What we need to show is that for any sequence with the limit an equal to a, we have as a limit fa of the images, right? And from this, we can conclude that f is continuous at a. All right, so this is a little bit more subtle, and we're going to use it using the technique of a proof by contradiction. So we use a proof by contradiction, which means suppose we have n to infinity an equals fa for all sequences an that converge to a, right? Suppose we have this condition, right? But on the contrary, suppose that f is not continuous at a. Well, what does it mean? Well, when f is not continuous at a, there's a kind of a jump, right? So I can, the closer I get to a, I can still find elements close to a that are far away from fa. Well, that's the intuition of the proof, and that's how we continue. So this means that there is an epsilon larger than 0, such that for all intervals, I can make intervals in, which is I minus 1 over n, a plus 1 over n, which are inside I. Well, let's assume, I just assume that all these intervals are contained in I, but I can choose n as large as I want to make it, to make in be contained in I. But the fact is, on each of these intervals in, I'm able to choose an element in this set for which the difference between fbn and fa is larger than epsilon. If I could not do it, if I could not find such an epsilon, then this would mean that f is continuous. But now I assume that f is not continuous. So I can, in any of those intervals in, I can pick a bn such that the difference of the function values fbn and fa is in absolute value larger than epsilon. Okay, now look a little bit closer at this sequence bn. Well, Bn is getting closer and closer to A, right? So the difference between Bn is enclosed and is contained in the set In. So the difference of Bn and A is at most 1 over n, right? So this means that Bn, being a member of In for all n, this implies that the limit for n to infinity of Bn is A. So if I look at this sequence formed by the elements Bn, I have a sequence that converges to A. So by assumption, we should have that the limit of Fbn should be A, right? So we should have, by assumption, we assume that any sequence that converges to A should, the corresponding images should have limit Fa. Yeah, but that cannot be true, right? Since we have that the difference between those elements is always at least epsilon. So the FBNs are not closing in on Fa, which is a contradiction, right? So that concludes the second part of the proof.